Okay, and we're go.
So, let's actually start something new today. So we have that first quiz, kind of tells you the kinds of things I expect you to remember at this point. So where we're going to pick up is at the beginning of chapter 7. Now, if you were in my class in the spring, today's class is going to be some sort of repetition, because we will be covering integration by parts, which was one of the last things I covered in my Calc 1 class. But I understand that most Calc 1 classes would not have covered it, so I decided I'll start there. Even though technically I taught it already, it's kind of unfair to just ignore it. Whereas with things like the exponentials and logarithms, I think that's pretty fair that I can skip those. So we are going to start with 7.1 of your textbook, integration by parts. Kind of keeping up the momentum. Probably the last thing you learned in Calc 1 was integration by substitution. So in chapter 7, we're going to go into a lot of other integration techniques, and this is going to be the first one. So I'm assuming you remember substitution and all that good stuff. We're just going to forge ahead. So, recall, a long time ago, there was something called the product rule. This basically said, if we had two functions multiplying each other, and we took the derivative of that, then it ends up being the derivative of one times the first one times the other plus the derivative of the second times the first. Now, what we can do here is we can integrate both sides of this expression. I'm kind of justifying something to you here. And the fundamental theorem of calculus tells us that this integral sign and that derivative, they kind of kill each other, right? There's going to be a plus c, whatever. Over here, integration distributes across addition, so you'll have two integral signs. So ultimately, if I integrate both sides, I would end up with something that looks like this. Fg equals the integral of f prime g plus the integral of fg prime. And I can solve for one of these integrations here. Let's say I solve for the integral of fg prime. I would get something like f times g minus the integral of f prime times g. Now there's a common change of notation here. If we set f equals u, we set g equals b, so your f prime we can think of as du, and your g prime we can think of as the derivative of b. Right, I'm forgetting the Leibniz, I'm mixing the Leibniz notation and the Newton's prime notation here. But then we would end up with the following formula. The integral of u dv is equal to u times v minus the integral of v du. This, my dear friends, is the integration by parts formula. And as you would notice, it reverses the product rule. So remember what integration by substitution was. That was just the reverse of the chain rule. Turns out we can also reverse the product rule. And the result of doing that is integration by parts. So let's actually, at this point, do a little example to see this thing in action. Example. X times e to the x. So how would you integrate that expression? So here's something that I think you should know. Let's just preface this a little bit. I actually don't remember how much I mentioned this in Calc 1. So let's just actually start. First of all, let's mention integration is going to be a big part of this course. So I want you to have a certain approach when it comes to integration. Because we're going to learn a bunch of techniques, you're going to want to be able to keep them straight in your head. And so knowing this approach might come in handy. So, one, right? Faced with a random integral. At least in Calc 2, I mean, it can get a lot crazier. The first thing you're going to do is you're going to try to apply a basic rule. Okay. And what are the basic rules? I am referring to the guys that tell you how to integrate several basic kinds of functions. So like you learned that towards the end of Calc 1. You learned this towards the end of Calc 1. You learned that the integral of sine of x was equal to the negative of cosine of x. Plus c, you learned that the integral of cosine of x was equal to sine of x plus c. You learned that the integral of e to the x is e to the x plus c. Basically, you learned a bunch of rules to integrate very specific kinds of functions, right? I refer to those as your basic rules, okay? So if you're faced with a random integral, the first thing I would do is do any of these rules, just apply it, right? And if they do, I would use them, okay? So if those don't apply, because they won't always, and pretty much in Calc 2, it's not very likely that I'm just going to ask you one of those guys. So probably the second thing you'd want to do is, if one does not work, try to simplify to use a basic rule. So that will happen every now and then. So for example, if you saw an integral like that, technically he doesn't look like those, but you can do a little bit of algebra to get it to look like those, right? You can just divide x to the fourth into each part, and then you can integrate each individually, right? So this one would look like that rule, so that becomes ln of absolute value of x. This one looks like that rule, so you just add 1 to the power, divide by the new power, plus c, right? So that's kind of the second thing. Now, the third thing is actually to try substitution. Right? So there are many integration techniques, but substitution is by far the easiest one of the sophisticated techniques to apply. So I quickly check if I can apply it. And remember, to check that if you can apply substitution, you're really looking for two things. You're trying to substitute something that will make the function simpler, and you need to make sure that the derivative of that thing is a factor somewhere else in the function where the constant factor doesn't really matter. Okay. And then now, fourth, maybe I'll do an indentation here, because there are a bunch of techniques that we're going to learn where they're kind of at the same levels. In by parts might be the next one. Or other technique. And so this list is to be completed later, but so far, here's how I want you to start thinking, right? So I give you a random integral. The first thing you're going to look for, does a basic rule work? If the answer is yes, just use it. If no, can I just simplify it to use a basic rule? If yes, do it. If no, does substitution work? That's always what you're going to ask yourself third. And then if not, you're going to try some other techniques where when we learn a bunch of them, I can group them according to certain priorities here. So looking at this, that's the first thing I would think about. Does this look like a basic rule? No, none of these guys look like an x times an e to the x, right? Can I simplify it to look like a basic rule? No, what are you gonna simplify here? So the third thing I would say, does substitution work? Well, does substitution work? How do you know?
Because the derivative isn't one of the other ones.
Well, it depends on what you're choosing, right? Why would substitution not work? Yeah.
Because the derivative of x is 1 and derivative of e to the x is e to the x, and there's not a factor in that equation. So.
Okay, well, what if I did, well, one thing we should have learned from Calc 1 is u equals x is always a bad substitution, right? That just changes all the variables, but leaves you in exactly the same situation. So the only real candidate to make substitution work here would be e to the x. So then you look at u equals e to the x. And now you might say, well, if I differentiate that, the derivative isn't somewhere else in the function. Now, let's get a little bit more sophisticated. There is something that we can still do to try to change the function here. And it's going to be a dead end. But I want you to actually think about step 3 seriously. Is there some way I can get this substitution to work? So, seeing that if I differentiate this, I'll get e to the x, and I won't have that extra factor. Or technically, I do have that extra factor here. So du would be e to the x dx, and I actually do have that here. So it means that this part here can become du. So now the question is, how would I write the x? The x will end up being ln of u. So I could apply a substitution here technically, and that's what I would get. So now the question becomes, do we know how to integrate ln of u? How would you integrate ln of u? Do we know the integral of ln? Yeah?
Isn't it x ln x or x or u ln u minus u?
It is. How did you do that?
I memorized it. It's primarily.
Good. We're going to do that later. This is not something you know how to do from Calc 1, right? We know how to differentiate ln, but we don't know how to integrate ln. So this kind of leaves us with a dead end here. So substitution, we kind of forced it to work, and it kind of left us somewhere where we don't know what we're doing anyway. But it's something that you should think about, at least, right? Because it can save you a lot of work. Sometimes I see students trying to do something else when substitution would have worked 10 times easier. Okay, but that's the thought process, how I want you to think about it. Does the basic rule apply? No. Can I simplify it? No. Does substitution work? No. That's when you start thinking of everything else, okay? So yeah, we would have ran through that thought process, and now we end up back here. Okay, so now let's think integration by parts. We'll deal with this guy a little bit later, so don't worry about it. Okay, how does this apply? So, again, let me recopy this formula, because you haven't memorized it yet. Do you remember how to actually apply this? Or maybe you might not do this in so the idea here is we want to compute the integral on the left by computing the right side. Now you'll notice that the integral on the left has two pieces to it. There's a u part and there's a dv part, which is the derivative of some function v. Okay? So here's the process is you would have to actually make the choice in the beginning. So you are going to choose your u and your dv. plug into the formula. And then 3, compute the right side. Which hopefully becomes easier. Okay, so, and that's integration by parts. So this is the formula, here's how you actually put it into practice. So, who would you actually choose to be the u and the dv in this situation?
X would be u, and e the x, the x would be the u.
Okay, so u equals x is always a bad substitution, but we're not doing substitution, we're doing integration by parts. So we'll set u equals x and dv equals e to the x. So now let's see if this will work with our formula. So we have u, we have dv, so I need to find what du is, and I need to find what v is in order to plug in the right side, right? So what I'm going to do is I'm going to differentiate this, so that's just 1 dx, and I'm going to integrate this, so that's just going to become e to the x, right? E to the x is e to the x. Forget the plus c at the moment, because we can deal with the plus c later. And so now, we plug in. And so the integral of x e to the x would be equal to, so here, this is the u and the dv. The result should be u times v minus the integral of v du. And we found the parts, we're going to plug them in. So the u is x, the v is e to the x, integral, the v is e to the x, and the du is just dx. So now you'll notice that we're in a situation where, in order to compute this integral, I have to compute this expression, which involves me doing this integral. And what you'll notice about this integral is it's easy, right? In the sense that it's a basic rule. There's a basic rule that works here. So here we'll have x e to the x minus the integral of that is e to the x plus c. And that would be our answer. Questions so far? So you see a random integral, you're going to think, does the basic rule work? No. Can I simplify it? No. Does substitution work? No. Okay, maybe integration by parts, depending on how it looks. You're going to try to apply this formula. Here's how you would apply it. And sometimes, if this method works out, what's going to happen is the integral on the right side is going to be easier than the integral on the left side, which would make sense a lot of the times because, as you would notice, differentiating the u function can downgrade its difficulty, right? So an x would become a 1, if it's an x squared, it becomes a 2x, if it's an x cubed, it becomes a 3x squared, etc. You can actually break down powers and things like that. So there's a lot of reason to believe the guy on the right will be easier to compute than the guy on the left. And here's one very simple example. So, and of course, here's something that you might remember for count 1. You can always, if you're ever not sure about something, you can check by differentiating this. So if you were to take the derivative with respect to x of x e to the x minus e to the x plus c, what would you get? Well, you do the product rule here. Differentiate the x, leave the e to the x, plus leave the x, differentiate the e to the x, minus differentiate the e to the x. Differentiate a constant, you get 0. Here you'll have e to the x minus e to the x, and you end up with x e to the x as the answer. So we know it's right. So that actually works. That's integration of parts. And we're done for that. I'm kidding. Okay, so that was a very simple example. The examples can get more complicated, and the examples can also get quite annoying, and so I'm going to also teach you a variation on this, using this formula in a little bit, but let's give you some information here. Now, how do you make the choice? Right? Who gets to be U? Who gets to be dV? Right? Because that might be something that you weren't sure about. Right? You might feel like, well, we kind of lucked out there, right? What if I had chosen the U to be the e to the x and the dV to be the x? Well, I would have ended up in a worse situation, right? Because I would integrate this guy to get an x squared. And I'd end up with an x squared e to the x over here, right? So it's kind of important that the choice we make. Does anyone know how we make the choice? Jog your memory. Yeah.
If u could be like, take derivative and becomes a constant, then that'd be a better choice than for u.
What if you're not in that situation?
Okay, usually in integration methods you have two functions, so you just look at both the functions, see which one will be easier to integrate.
How do you know?
You can just do it mentally, right? Like, see-
Okay, well, comparing x and e to the x, who's easier to integrate? They're both equally easy,
Okay, in that case.
right? Yeah.
Use the Liate.
Liate is how we do it. So that's just a mnemonic. The answer. Like someone really thought about this process and came up with a mnemonic to remember. It's called Liate. It's short for a word. You should think of it vertically. So it's called Liate. And how you apply Liate is the higher in the ladder you are, choose to be U first. And as the more you move down in this list, you would choose those guys to be U last. Okay? So this represents the kinds of functions you'll usually encounter in a Calc 1, 2, or 3 course. L stands for logarithms. I stands for inverse functions, including inverse trig. A stands for algebraic, which here they mean polynomial. Right? But lipstick doesn't really roll off the tongue, you know what I mean? So they throw an A in there. T stands for trig functions. E stands for exponential functions. Right? So whenever you have a product that involves these different kinds of functions, you choose your U based on who is higher in this list. So for example, if in the event just now where we had the integral of x e to the x dx, you'll notice that the x falls under the A category, while the e to the x falls under the E category. A is higher in the list than E, so you choose this to be U. Right? Following this list, you always end up in a situation where the right side is, at least in theory, easier to do than the left side. Right? So you're not going to make the right side more complicated. Not that you'll always be able to solve it, but you'll have a better chance of solving it by following this. So it's called Liate, and that's how you make the choice. So we have the integration by parts formula. We have to apply that formula. In order to apply the formula, we have to choose these functions, and Liate is how you would make the choice. Okay, so let's do another example. Try that one. to learn how to integrate ln x. So we look at this, does the basic rule apply? No. Can I simplify it to make it look like a basic rule? No. Does substitution work? Well, if I try to apply substitution, I'd end up getting an e to the x times ln of x all squared, and that's kind of weird, or something similar to that. And that's worse to me. So you might start thinking integration by parts. Now once you start thinking integration by parts, how do you choose the pieces? What would you be here? Yeah?
According to that, it should be ln x, right?
It should be ln x. Now to go by what's easier, it's pretty easy to differentiate x squared, but that's not how we're making the choice. dv then, by process of elimination, will be the x squared part. What's the derivative of ln x? 1 over x. And what's the integral of x squared? X cubed. Okay. Now at the moment you might, oh my god, we made it worse. Well, hold on. Let's actually plug this in here. And it is going to be u times v minus the integral of v du. So this is x cubed over 3 times 1 over x. So yeah, this bumps up in a power, but it ends up not being complicated anyway, because this actually simplifies nicely here. So I have x cubed over 3 ln x minus the integral of 1/3 x squared. And that's easy to integrate. That the basic rule will apply here. So that becomes 1/9 x cubed plus c. And of course you can check that one. That would actually be the integral here. If you differentiate this, you'll actually get that. Questions? That's a lot. Don't worry, we'll start to do really fun integrals pretty soon. Don't worry, it's day one. How do you do this one? Yeah.
You can make ln x u and then dx dv.
Right. So that's often something that people never think of, because they kind of see that, well, there's only one function there, isn't there? But technically, you can always think of a 1 being here and choosing 1 dx being the other part, right? So in this case, your ln clearly is the L part, and the 1 dx will be the A part. And according to Leote, the L is still going to be the U, and I will just have the other part be the dv. So U would be ln x. My dv will actually be 1 dx. If I differentiate this, I get 1 over x dx. If I integrate this, I would get x. And so, plugging this in, we get u times v minus the integral of v du. The x's of course cancel. This is the integral of 1. We get x ln x minus x plus c. And that's where the formula came from. He was like, I just memorized it. Which, not to knock him, I totally agree with that approach. This is something that you should have memorized. So I will write this down, and from now on, from henceforth and forevermore, this is a part of your basic rules list. The integral of ln should be something that you have memorized. But if hell freezes over and you forget, you should be able to derive it also. So the integral of ln x is x ln x minus x plus c. And we can derive that using the integration by parts with a little sneaky trick here of thinking as one as being the other function. Okay, let's this one. Integrate sine inverse. Okay, how would we do this? Yeah.
U is arc sine.
Yes, and by the way, this is AKA arc sine. We can do U is arc sine. And hence our dv will again be like 1 dx. And you don't really have to write the 1, sometimes just writing dx makes you feel uncomfortable. What is the derivative of sine inverse?
One over radical 1 plus x squared.
1 minus x squared. Close. Okay. Integrate 1. Well, that's just x. So the integral of sine inverse of x dx is going to be u times v minus the integral of v times du. How do we continue? How do we do that guy?
We'll bring it out.
Just use quotient rule.
What do you mean quotient?
Oh, this is integrated.
Yes, this is integration, yeah.
So if you convert that to like, that whole thing to like the negative 1/2 at the top and then sort of like, put the x in and make it all like the 1, make it like all.
So x times 1 minus x squared to the minus 1/2,
Right.
and then do what?
And then, would you have to use this rule again or something?
I don't know, I'm asking you.
Use substitution?
Substitution. Again, every time you see an integral, you go back over that list in your head. Here's a new integral, what do I do now? Does it look like a basic rule? No. Can you simplify it to look like a basic rule? No, because you can't really expand the negative 1/2 power. At least not now. Later on in this class, we're going to learn how to expand that. It's going to take an infinite number of terms, not kidding. The third thing I'm going to think, substitution. Can that work? Yeah, there's a 1 minus x squared, the derivative of that is a constant times x. Substitution is how I would approach this one. So here I'm going to do now u equals 1 minus x squared. I'm doing a substitution, not integration by parts. Right? Of course, the moral of the story is that every time I teach you a new technique, you can mix and match them. You might have to do one technique on top of another, on top of another, and you're always going to need to know every time you see an integral, what's the best technique to use, what can work, what won't, and thinking according to that strategy that I mentioned, the partial strategy that I gave so far is going to help you. Every time you see another integral and you want, well, how am I going to do that? Start over, think along those lines. So substitution works here, your du will be minus 2x dx, which means that your minus 1/2 du would be the x dx, which means this becomes, this would end up being a positive 1/2, and this will end up being a 1 over radical u du, which we can write as u to the minus 1/2, Because again, that's another random integral, so I'm going to ask myself, does a basic rule apply? Well, no, not really. Can I simplify to look like a basic rule? Yeah, I can use the laws of exponents to write it as a power function. And ultimately, I can now just do the integration with that. Add 1 to the power, we get 1/2. Divide by the new power, same as multiplying by 2. So I get 2 times that times 1/2, of course, plus c. And as we've learned, we need to replace du with what it is. So this one ends up being x sine inverse of x plus 1 minus x squared to the 1/2, or radical of 1 minus x squared plus c. Questions on that one? So yeah, that integral you get, it's not always just going to be a nice, easy peasy integral. It might require a different technique. And so we're going to have to get very good at the technique. Hopefully by the end of chapter 7, we'll be awesome at many techniques. That's the goal anyway. Something I want to mention here, which I mentioned to my Calc 1 class, but I'll mention it again here. We also think of substitution in a very narrow way, in the sense that we're always substituting u equals something. In Calc 2, we're going to be doing other kinds of substitution. But even your regular substitution from Calc 1, you do have the option of thinking of that in slightly different ways. So, for example, instead of doing u equals 1 minus x squared, I could do u squared equals 1 minus x squared. And now, what would be the benefit of doing something like that? Well, it can kind of make it easier in terms of radicals. Because if I make under here a square, what's going to happen is it's going to cancel the radical. Or you can think of it as making u equals the radical of this guy, then squaring both sides. Either way, you don't have to do a u substitution, you can do a u squared substitution. Or a u cubed substitution. Or you can make this left side any convenient expression to simplify this integral. But I'm just easing you into that idea very slowly with a simple substitution. And now what you would do is you continue the substitution process. You're just going to differentiate like you normally would. Derivative of u squared,
2u du.
2u du, chain rule, and derivative of that is minus 2x dx. Now what's going to happen is your minus u du would become x dx here. And so what you can do is this x dx here, you'd replace with minus u du. This part here would just be replaced with u. Then what you're going to have is, when I start plugging these guys in, I would have the integral of minus u du divided by u. These guys cancel, and I just have -1, right? Which is like easier than this one, right? That's the whole point of doing this kind of fancy substitution. Integrate that with respect to u, I would get -u plus c, but what is u? Well, if I solve for u from here, I get the square root of 1 minus x squared, so I get the negative of the radical of 1 minus x squared. Right, which coincides with this. There's a positive there, but it's because there was a negative here. But yeah, just an alternative. You want to kind of expand the way you're thinking of substitutions. You don't always just have to let a single variable be a substitution. You can actually make that variable behave in other ways and just differentiate both sides as you normally would, remembering the chain. We're going to be extending this idea a lot as we move on. So when we do like trig substitution, and they're like Weierstrass substitutions, where you let the guy on the left side be this crazy thing to make the whole integral work out a little bit nicer. Let's actually segue into the next section by considering this one. How would you do that? Okay, let's do it together. Does it look like a basic rule? No. Does it look like a basic rule? No. Substitution's gonna work? No. Okay, now we're at integration by parts. Let's do it.
So your u would be x squared.
Right, because that's an A and this is an E, and A is higher in the list than the E. And so your du is going to be 2x dx, your v is going to be e to the x. So you're going to get x squared e to the x dx equals u times v minus the integral of v du. How would you do that integral? Well, technically, we've already seen that. I can factor out the 2, but let's pretend we didn't do that the first example. You would have to actually do integration by parts again, right? That would be the more convenient thing. So here you're going to say u equals x. I would probably factor out the 2. dv equals e to the x dx. Then my du would be dx, and then my v would be e to the x. And so what I'm going to do now is this is going to become x squared e to the x minus 2 times u times v, x e to the x, minus the integral of v du, e to the x dx. And then I can come down here and integrate that and expand the parentheses. And I would get that. So again, integration by parts could be something that you'd have to apply over and over. It just depends on what this integral looks like that you get on the right side. Okay, what about this example? How do you think that one's going to play out? Keep repeating it, right? You're going to do integration by parts, break it down to an x to the 4th e to the x, do it again, x cubed e to the x, do it again. Have integration by parts is going to start spreading out. You're going to have all these nested parentheses. You're going to have to make sure you're distributing like a lot can go wrong here. So here you'd have to repeat five times int by parts, which, needless to say, is very annoying. Okay, and just to have a little teaser there, there's a better way. Which we'll get to. But if that example alone doesn't convince you that integration by parts works, but it can be annoying sometimes, consider this example. How do you do that one? So let's start. Right, so first thing you think, does the basic rule? No. Can I simplify the basic rule? No. Does substitution work? No. Think integration by parts? Okay. Who gets to be the u? Who gets to be the dv? This is a t, this is a e, so I would choose u to be the sign of x. Choose dv to be e to the x dx. du would be derivative of sign. Cosine x dx. v equals e to the x. And so what I would have is e to the x sine x dx is equal to u times v minus the integral of v du. am I gonna do this guy? Okay, let's do it again, see what happens. So I would choose here, u equals cosine of x, dv equals e to the x dx. So my du is going to be minus sine x, and my v is going to be e to the x. So let's do integration by parts again. So this is going to be e to the x sine of x minus, in parentheses, or in parentheses because of the negative sign, u times v minus the integral of v du minus the negative sign becomes a plus e to the x sine x dx. Okay, how are we going to do that guy? Yeah?
So it equals the original equation and move the one that just got on the other side.
Right. Now the answer is not to do integration by parts again, because we've been here before, right? At this point you're going to notice, like, what happened? Am I just going to be here forever doing it over and over and over and over again? And the answer is no. The trick with this kind of situation, which, you know, at this point you're like, well, that's weird, right? But it happens. The trick here, how you deal with this sort of situation is you would set it equal to the other side, and just notice that this thing now becomes an expression that you can solve for, like algebra, in an algebra equation. You don't have to do this, but people like doing this. They just like to call that a letter. So if they set I equals this integral, what you just realized is that I is equal to e to the x sine x minus e to the x cosine x plus I, right? And at this point, that's now just, that's an algebra equation. I can solve for I. So I'm going to multiply this out by the negative sign. I get negative I over here. Move it to the other side. I would get 2I is equal to the e to the x sine x minus e to the x cosine x. And of course, here we put a plus c because we know it should be there. We prematurely cut this short, so we didn't get the plus c popping out naturally. Just kind of, yeah, when we integrate, there should be a plus c somewhere. And at this point now, we can just divide by 2. Sine x, yes, cosine x plus c. Of course, c divided by 2 is just another constant, so we can write that. And that will be your answer. But now you're in the situation where now I'm worried. What if this starts to happen like 5 steps down and now I have to cycle back and go back up and read? You can get into a situation like this pretty easily as well. So another potential issue with integration by parts. Let's talk about the nicer way. There's a better way. Where we won't have to worry about these nested parentheses and applying this formula over and over again and doing all this stuff. And the idea here is to turn int by parts into an algorithm. Just by noticing how it operates. Now I'm just going to tell you the algorithm because we only have like 15 minutes and I want to actually get through a couple of examples. So I'm going to tell you this algorithm that can replace integration by parts and kind of deal with these annoying issues in a less annoying way. And in fact, you can completely replace integration by parts with this method. It will work in every instance that integration by parts will work in. And it is called tabular integration. So, it's not really a nice way to describe it, but I'm going to describe it as best as I can in a nice way, and then we'll do a few examples and it's going to be easier. It's called tabular because you're going to actually set up a table to actually do everything. So given, let's say you have the integral and you have two functions multiplying each other, f and g dx. Set up a table below it in the shown way. Okay, so here's how we're going to set up this table. I'm going to arrange it so that the guy who's going to be my u is in the first position and the guy who's going to be my dv is in the second position. So if they're not in the right order, I'm going to swap them. And I'm going to create a table. Dot, dot, dot. This table is going to have n rows in it, and I'm going to let you know what n has to be for the particular problem. So, what you're going to do with the u is you're going to keep differentiating it. Right? So I would get f prime, f double prime, f triple prime. I'm going to differentiate this n times, where we know the notation for that is just f to the n with the parentheses around the power. That's a shorthand for the nth derivative. And I'm going to integrate the dv's like I always had to do. But I'm going to actually keep integrating, just integrate over and over and over. And so what this part will look like is that there's not a like nice notation here. So what I'll do is like subscripts. So G1, G2, G3 goes all the way down to Gn. So that's where f to the n equals the nth derivative of f, and g sub n equals the nth integral of g. So first we're going to set up this table. Now how long does this table have to be? Dot, dot, dot. I'm going to tell you specifically how long afterwards. There's one more thing to actually do. What you're going to now do is you're going to multiply along the diagonals, starting with the f, multiplying the g's. So what's going to happen up here is you're going to have the f to the n minus 1 multiplying this g here. And then I'm going to multiply here across there. Okay? We're not done. One more thing. Because we would have those nested parentheses where the negative sign is distributing, the negative sign is going to change the sign. Every time there's a nested parentheses, the sign of everything inside is going to change. So you're going to actually alternate the sign to get that to happen. So here, I think of this as the positive product. Here, I think of this as the negative of the product. Here, I think of this as the positive of the product, etc. Right? So here it's going to be plus or minus. Here it's going to be plus or minus, but it depends on how long the table is, what it's going to end up being. Okay, so that's the construction of the table. We're going to do a few examples. Now, here's the answer. You're going to actually take all these products. So the integral of f times g dx is going to be equal to f times g1 minus f prime times g2 plus f double prime times g3 minus dot 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 dot. I was very tempted to do that thing that Colbert does when he's reading the president's thesis. Da 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 da. Okay. So this is going to go on for some time, but eventually you're going to end up with plus or minus the f to the n minus 1 times g to the n. And then for the final one that goes across here, that one is dealt with differently, right? So for that one, we're actually going to integrate the last product. So based on whether this is plus or minus, this is going to be plus or minus, and you're going to have the integral of f to the n gn dx. And that's how you end it. Now, it might look complicated at the beginning, but once you actually see this working through, you're going to realize how easy it's going to be. How do you know n? That's how long does the table have to be? Well, here's how you know. Stop the table when one of three things happen. One, if f eventually goes to 0, right? So this is going to happen if your f is a polynomial, right? So if you start with an x to the 4th, eventually you keep differentiating that, it's going to go to 0. Stop the table at that point. That's one situation. 2, if fn times gn is the original integrand. So that covers the e to the x times sine x case. Eventually, if you start doing this table and you realize there is a row that looks exactly like what the original integration looked like, it might be off by a constant, but you ignore that part because you can always factor those out. But if you start to get back the original fg, you would stop the table at that point. The third one is just, if neither of these two things happen, you pretty much stop the table when you're confident that this last integration is going to be pretty easy. I can see clearly that I can do a substitution here or something else. If the integral of f and gn dx looks easy in quotations. Okay. Let's do one of them. Well, we're going to do a few examples. I don't know how many we'll get through in the remaining time. Let's do this guy, x to the 5th e to the x, which hopefully you guys have some appreciation for how annoying that's going to be. If you don't have an appreciation for it, actually do it using what we were doing before, and then you'll start to appreciate how annoying that actually is going to be. With tabular integration, how would it work though? Well, that's going to be my u, that's going to be my dv, so it's already in the right order. I'm going to start setting up a table. I am going to keep differentiating the x to the 5th. Differentiate that, I would get 20x cubed. Differentiate that, I would get 60x squared. Differentiate that, I would get 120x. Differentiate that, I would get 120. Differentiate that, I would get 0. I am now in a situation where I eventually hit 0, and what you do here is you stop. Right? Once you hit 0, you're in case 1, stop. Stop the table. So if you realize that's going to happen, which you kind of should know that by what the thing you have here, it's a polynomial, it's eventually going to hit 0. Then what you're going to do is, you're going to keep integrating the e to the x. Well, that's easy, that's just e to the x all the way down the line. Just bring that down until the last row that you just ended up with. Right? So this table ended up being 5 rows long. Now what you're going to do is you're going to do these multiplications. Plus sign here, minus sign here, plus sign here, minus sign here, plus sign here, minus sign here. And of course this times that will actually give you the integral of 0, which is just c. Right? So you actually don't have to even worry about that integration. Yeah?
Why do you start with a plus sign?
Because the first thing is going to be the u times the v with a plus sign.
Oh, okay.
Right? But then because you minus the integral, it's going to change the signs of, it's going to alternate signs starting right after that. So this first multiplication is the u times the v.
Yeah, it makes sense.
And that's how it starts off. Right. So now, I'm gonna move over here because I don't have space over there, but we're done. Now all I have to do is write down that list, and that's the integral. So from this I can see that the integral of x to the fifth e to the x dx is plus x to the fifth e to the x minus 5x to the fourth e to the x plus 20x cubed e to the x minus 60x squared e to the x plus 120x e to the x minus 120 e to the x. And technically here, you would have the plus the integral of 0 dx, but we already know that that would just be a constant. And so that's where your plus c is going to come from, but that's the answer, right? And hopefully now you also have some appreciation for how annoying it would have been had you done it the other way. Of course, you can factor out the common e to the x after this, but I don't particularly care at this point if you want to spend the time to do that. But that's the answer. So we can do 5 integration by parts relatively quickly. This is pretty quick. It's going to be a lot quicker than actually writing out all those lines and putting parentheses all over the place. So we have about 5 minutes left. I'm not really going to do anything else, but what I will do is I will leave you with some examples that I want you guys to try, and we will actually do them tomorrow. Make sure you try them on your own. We'll pick up with this tomorrow, and then once we're done with these, we'll jump into another integration technique. E to the square root of x. Right? E to the x squared has no antiderivative, but e to the square root of x surprisingly does. X cubed, e to the x squared. Tan inverse of x. X squared ln x, we already did this, but try the tabular method with this to see if you know how to do that. And tomorrow what I'll also probably do is I'll probably redo the things we already did using the tabular method and show you that it actually works in all these situations. What about x squared, e to the x cubed, f square root of x cosine square root of x, g x cubed sine x squared. So try those for tomorrow. We'll wrap up with those and then move on to the next section. So chapter 7 is all about new integration techniques, which you will be using in the future. Any questions on anything we did so far? Yes.
So for all the examples you try, you can use this chapter.
Yep. You can even try doing it that way if you'd like, although you might have to do something first. But I'll actually redo the examples using Tabular method. It should be pretty quick. And I'll see you guys tomorrow.